Imagine standing beneath the night sky. The twinkling stars and the glowing band of the Milky Way seem to make up the entire universe. Yet in reality, what we can see is only a tiny fraction of it. About 95% of the universe consists of things we cannot observe directly: dark matter and dark energy. These invisible forces are constantly shaping the fate of the cosmos, and they continue to puzzle scientists to this day. In this video, we'll take a deep dive into dark matter and dark energy, from their discovery to their profound impact on the universe, gradually uncovering their secrets. Join me on this journey into the unknown and discover how these hidden forces govern the reality we live in. Dark matter is a form of matter that does not emit light, does not reflect it, and does not interact with electromagnetic radiation. Unlike ordinary matter, it is not made of atoms or molecules, but reveals itself only through its gravitational influence. We know dark matter exists because the motion of galaxies and galaxy clusters cannot be explained by visible matter alone. As early as the 1930s, astronomers noticed that stars within galaxies were orbiting at unexpectedly high speeds. If only visible stars and gas were present, these galaxies should have torn themselves apart. But they did not. This suggests the presence of an unseen form of matter providing extra gravity and holding everything together. Dark matter may be composed of unknown particles, such as weakly interacting massive particles or axions, yet it has never been directly detected in a laboratory. It does not participate in the strong or weak nuclear forces and interacts only through gravity, making it one of the most mysterious components of the universe. Today, it is believed to account for roughly 27% of the universe's total mass and energy. The evidence for dark matter comes from multiple astronomical observations. One of the most important is the rotation curves of galaxies. Stars at the outer edges of galaxies orbit at nearly the same speed as those closer to the center, a result that contradicts Newtonian gravity unless additional mass is distributed throughout the galaxy. Another line of evidence comes from the dynamics of galaxy clusters. Massive structures such as the Virgo cluster contain galaxies moving so fast that, without dark matter, the clusters would have dispersed long ago. Gravitational lensing provides even stronger proof. When light passes near massive objects, it bends, distorting the images of background galaxies. The degree of this distortion is far greater than what visible matter alone can explain. Fluctuations in the cosmic microwave background also reveal that small density differences in the early universe required dark matter to grow into the large-scale structures we see today. In addition, missions like the European Space Agency's Gaia satellite have mapped the motion of stars in the Milky Way with extraordinary precision, further confirming the existence of a vast dark matter halo. Together, these observations have turned dark matter from a hypothesis into an accepted reality, even though its true nature remains unknown. Dark energy is even more enigmatic. It is not matter at all, but a form of energy that causes the expansion of the universe to accelerate. While dark matter pulls things together through gravity, dark energy has a repulsive effect, driving space itself to expand faster and faster. Scientists believe it may be related to vacuum energy arising from quantum fluctuations or to a dynamic field often referred to as quintessence. However, the simplest explanation treats dark energy as the cosmological constant, a term introduced by Einstein in his theory of general relativity. Dark energy makes up about 68% of the universe's total energy density, far more than dark matter and ordinary matter combined. It does not clump together in specific locations, but is spread uniformly throughout space, making it impossible to detect directly. Instead, we infer its existence from its effect on cosmic expansion, a force that causes distant galaxies to move away from us at ever-increasing speeds, pointing toward a future universe that is colder, emptier, and more isolated. The discovery of dark energy emerged from observations of distant supernovae. In 1998, two independent research teams studied Type Ia supernovae and found that the expansion of the universe was not slowing down, but accelerating, a process that appears to have begun around 5 billion years ago. This result contradicted gravity-dominated models of the universe and could only be explained by the presence of a repulsive force. Follow-up observations using the Hubble Space Telescope and other instruments confirmed that the farther away a galaxy is, the faster it is receding, and that this acceleration is increasing over time. Studies of the cosmic microwave background, particularly data from the Planck satellite, show that the universe is geometrically flat. This requires the total energy density of the universe to be extremely close to a critical value. Visible matter and dark matter alone fall short, leaving dark energy to make up the difference. Measurements of baryon acoustic oscillations, along with weak gravitational lensing surveys, provide further support for an accelerating universe. As a result, dark energy has become a central pillar of the standard cosmological model, even though its origin remains unclear. Together, dark matter and dark energy dominate the evolution of the universe. In the early universe, dark matter amplified tiny density fluctuations, allowing galaxies and galaxy clusters to form. Without it, the universe would be nearly uniform, unable to give rise to stars or planets. Dark energy, on the other hand, takes over at later times, accelerating cosmic expansion and increasing the distances between galaxies. In extreme scenarios, this could eventually lead to a Big Rip, where all cosmic structures are torn apart. Their influence extends into efforts to unify particle physics with general relativity, inspiring new theories such as string theory and quantum gravity. Understanding these forces is crucial for predicting the ultimate fate of the universe and for improving the precision of astronomical observations. Yet fundamental questions remain unanswered. What exactly is dark matter made of? Is dark energy truly constant, or does it evolve over time? Solving these mysteries could reveal the existence of extra dimensions or even a multiverse. These invisible rulers remind us that the universe is far more complex than what we can see. Although dark matter and dark energy remain unsolved mysteries, scientific progress continues at full speed. Future missions such as the European Space Agency's Euclid telescope will measure the large-scale distribution of galaxies with unprecedented accuracy, helping scientists trace the evolution of dark energy. Deep underground experiments are searching for direct signals of dark matter particles, while theoretical physicists are developing new models to incorporate these forces into unified theories of nature. One day, we may be able to detect them directly, fundamentally transforming our understanding of the universe. If you're fascinated by the mysteries of the cosmos, don't forget to subscribe and like the video. I'll see you in the next one.